Hello, everyone. Good morning, good afternoon. Let me quickly briefly introduce myself first before we start. I am Ritika Vidhya. I work as a data scientist at Johnson & Johnson. I have more than 9 years of experience in the field of data analytics and machine learning. I've also been hosting training and mentorship programs for over 2 years now. I provide training in Python, Tableau, business statistics, and machine learning algorithms. So that's pretty much about me. Thank you everyone for joining today. I am going to speak about ensemble techniques in machine learning. I'm going to share my screen and then we can quickly have a look at the agenda for today. The first 30 minutes of this webinar, we will dedicate it to understand the entire process of Ensemble. What is it about? How does it work? What are the different methods? And we shall learn about the most popular techniques that are used in Ensemble learning, bagging and boosting. We'll take some examples and try to learn in detail about these two techniques. In the next 15 minutes, we'll have a quick live demo in Python. We'll go over a small example and we'll try to implement any of these algorithms in Python. And the last 10 to 15 minutes, we'll keep it for your queries or questions. So if you have any questions or doubts throughout the session, you could either put them in the chat window or you could ask me towards the end of this webinar. All right. So let's start with the overview first. What is Ensemble exactly? Ensemble literally means a group producing a single effect. And in machine learning, it does exactly the same thing. It is a technique that combines several base models, rather several weak models, in order to produce one optimal model. Now, there could be multiple sources of errors when we speak about machine learning algorithms. It could be noise, it could be variance, it could be bias. And Ensemble techniques help to minimize these error-causing factors and thus ensuring accuracy and stability of the machine learning algorithms. Now, how is it done? We'll learn that later. First, let us try to understand in detail with the help of few examples what exactly is this concept about. So let us talk about two kinds of learners in machine learning. There are weak learners and then there are strong learners. What are they? So weak learners have low prediction accuracy. They are as bad as random guessing. They are very prone to overfitting, which means they are unstable. So if you build a model, a classification model, and the model is unstable and it is prone to overfitting, it would not be really able to classify data that varies too much from the original data set. If we consider an example, let us say that you are training a model that identifies animals with pointed ears as cats. Now, if the model comes across any cat whose ears are curled, it might just fail. It won't be able to recognize because the characteristics through which the model was doing its job was pointed ears. It is totally unaware of curled ears. So it would fail. Strong learners, on the other hand, have a higher prediction accuracy. They convert a system of weak learners into a single strong learning system. How? Now, let's say there are two weak learners here. The first one, again, same, it identifies cats with pointed ears. The second one can guess the cat-shaped eyes. It can guess a cat. This is the cat-shaped eyes. They are two weak learners. Now, if we combine them, what would happen is after analyzing the image for pointing ears, it will then analyze for cat-shaped eyes, which in total would improve the overall system accuracy. That's the beauty of ensemble techniques. You can ensemble methods usually take advantage of the blended output from a number of weak learners. So it will learn something from one model, something from the other model, eventually combine all the predictions and make a final call. That is the entire concept of ensemble techniques. Let us have a look at one more example here. Let's say there is this group of blindfolded people and they are told to explore, touch and explore a mini donut factory and then share their personal experiences. Now, this mini donut factory, none of them has ever seen before. So basis their experience with that particular part of the machine that they got to explore, they would only know that part of the machine. Now, when we go to them and talk to seek feedback, each blindfolded person would only be able to talk about their experience. But when you combine their experiences, you might as well get a highly detailed account of the entire product, entire machinery part. And that is what ensemble techniques is all about. It would combine, it takes advantage of all the weak blended output of weak learners, which as compared to a solitary model, a lone weak model would be superior and hence would increase the prediction accuracy. No, Parna, strong learner can be strong on its own too. Here, a strong learner we are talking about in terms of ensemble. How does ensemble makes we convert multiple weak learners into a strong learning system? All right. Now let's understand the process. How does it work? So we are going to start with what's usually given to you, a data set. When you do any sort of analysis or when you begin with any analysis, the first thing that is given to you is data. The next step in model building is always to split your data into training and testing. So major chunk of the data, we usually keep it for training, and a small portion of the data is reserved for testing your model on the unseen data. These are the steps that we usually do. What happens in ensemble techniques is random samples are withdrawn from this training data. All right. These samples are withdrawn randomly. That you could define the sample size, and n number of samples would be withdrawn from these from this training data, and then individual models would be trained using these samples. So model 1 would take this random sample and it would be trained on only this sample. Model 2 would only on this part of the sample, model 3 this one, and there would be n number of models which would be trained on nth sample. That's how it works. Now these individual models have to be very different from each other, which eventually in turn, what would make how would that would be possible if these random samples are independent of each other? This sample should have nothing to do with the other one. If these samples are independent, the models that you will run would eventually be very different from each other. Now that is one of the necessities that you have to ensure if you want your ensemble method to be effective enough. All right, so far we split our data into training and testing. Using the training data, we have drawn random samples, and using these samples, we have built n number of models. Now, each of these models is going to have a prediction of its own. This would give you some predicted values. This would give you a set of predicted values and so on. So each of these models is going to give you some predictions, and then towards the end, you could combine all of these predictions to make one final call, one final prediction. This is how ensemble methods work in a nutshell. Now, a thing to remember here is the sampling that is done here, this is sampling with replacement. All right. So the samples that are withdrawn, these are withdrawn with replacement, with repetition. Now, what is sampling with replacement? Sampling with replacement means if a unit is withdrawn from a data point is withdrawn from the training data, it would be recorded here first, and then it is returned to this training data bag before the next unit is withdrawn. You withdraw a data point, record it here, and then you bring it back here. So the next time when you have to choose another data point, the first data point, you would see it again. You can choose it again as well. That is your sampling with replacement. Now, why do we need sampling with replacement here? What is the reason for that? Reason being, number one, if you do not withdraw samples with replacement, the size of the data set would eventually decrease. You might have to throw a lot of data to have that diversity here. As I said before, there has to be a lot of diversity between these random samples, and you would eventually have to throw a lot of data here if you want enough diversity, if you do not draw samples with replacement. So number one, we do not want the size of the data set to be decrease. Number two, it helps to make base models independent. As I said, when you sample with the replacement, the samples that are generated, they are independent of each other. Each of these samples would be independent of each other, which would make it more diverse, hence making the models independent of each other as well. So that is this entire process. A few things to keep in mind. Number one, n number of models are generated out of n number of random samples which are withdrawn with replacement. And number two, the predictions towards the end are combined to get final prediction. This is the entire idea of ensemble methods in machine learning. All right, now let's talk about the different methods that are used. So the popular ones are bagging, boosting, and stacking. Bagging and boosting are somewhat of the similar idea, where you could actually combine multiple weak learners of the same kind. Stacking, on the other hand, would allow you to combine models of different kinds as well. For example, with bagging, if you have, if your base model, if your initial model is decision trees, you will be only able to probably collect 10 different decision trees and put them together in bagging. Or if you start with a random forest, you can do it with random forest. But with stacking, you could have a random forest and you could top it with another extreme gradient boosting algorithm, which you could further top it with another algorithm. So models of different kinds could be stacked together. Bagging and boosting, the models have to be of the same kind. Now let us try to understand what bagging and boosting are all about. We won't be talking a lot about stacking today. We'll just focus our study to bagging and boosting for today. All right, let's talk about bagging here. So from going back to the previous slide where we talked about sampling with replacement, in data science or in machine learning, sampling with replacement is called bootstrap. The process is called bootstrapping. So withdrawing random samples from the data with replacement is called bootstrapping in data science. The other step which we saw here in the previous slide was that towards the end, we combined the prediction of different base models. These combining predictions is done with the help of aggregation. We use an aggregation function at the end to combine multiple predictions. Now, how to do that? I'll show you with the help of certain examples. But these are the two basic steps that we had talked about: bootstrapping and aggregation, which combined together means bagging. So bootstrap plus aggregation is bagging. The only thing to remember here is, in bagging, all your models run in parallel. All the models run in parallel. Okay. So from model 1 to model n, if you could recall the figure from the previous slide, all those models would be running at the same time. They would be predicting certain values, and then an aggregation is applied to take a final prediction. Now, the next thing to remember here is, now there are two kinds of problem that we try to deal with in machine learning. The first one is classification, where we classify data into multiple labels and then regression. Regression we use for continuous variables. Aggregation function for classification is mode. We usually use mode for classification and then mean for regression. Now, how to go about that? Let us take an example and understand this thing here. So we'll talk about regression first. Okay. So we have two models here, model 0 and model 1 and model 2. All right. Model 1 is as simple as average, the average function. So y would be the predicted value is always going to be, an average of all the x's here. So that's your model number 1. Model number 2 is a slightly complex model. It says your y would be average plus minus standard deviation. So these are the two different kinds of models that we are going to work on here. You have the actual value here, and then basis this function over here, you have the predicted value. This is what you usually see in any sort of model, in a regression model, an actual value and predicted value. What is an error here? Error is the difference between these two values. My actual value was 2.6, but the model predicted a 3.3. So my error becomes, I'm going to use an absolute function here because we do not want any positive or negative numbers. This minus this. That is your absolute error. So I'm going to calculate this error for all of these values. And with that, my mean absolute error for these 10 observations becomes 0.98. That is the mean error of all these 10 observations. You could also calculate the percentage error. Percentage error is nothing, this divided by the actual value. So here comes your percentage error, which will allow you to calculate the mean absolute percentage error. So model number 1, mean absolute error is 0.98 and mean absolute percentage error is 30%. So the model is able to predict within 30% of the error. That's what it means. Now let's consider this another model, which we saw. It's a little complex. We have predicted values. We have tried to put a correction here. The correction is nothing but the standard deviation. Using that, we have certain set of predicted values. Let us calculate error and just put this over. Okay, let's calculate it here. I'm going to use the absolute function again, and it is predicted minus actual value. That's your error. And these are all the errors. Let us calculate the percentage error here. Model number 2, my mean absolute error has further increased to 1.19, and the percentage error is now approximately 35%. First model, 0.98, percentage error is 30%. Second model, 1.19 average error, and your percentage error is approximately 35%. Now, what did we, when we were talking about bagging, we saw that we run individual models and then towards the end, we combine the prediction. How can we combine our prediction here? For regression, we use a mean to combine. So mean means average. So all we need to do here is we'll take an average of both the predictions. Prediction number 1 and prediction number 2. Take an average. That is your combined prediction here. All right. Now let us again calculate the error. My error is going to be this minus actual value. The actual values are same in this case. So let us use an absolute function here. So this time I'm not using a separate model here. All I have done is I took an average of these two predictions. Let us see what impact is created on the error and what impact has been created on the percentage error. So as you all can see, my absolute error has gone down to a 0.8. From 1.19 to 0.98 to 0.8. So mean absolute error has gone down and percentage error has gone down to 19%. And thus my accuracy of the model has increased. This is how your aggregation works in regression. Okay, mean for continuous variables. All right. Now let us see another example for classification. So what happens in classification problem is you classify labels. Let us say we have these 10 records. These records have been labeled as 1 and 0. These are the actual values, actual labels. All right. Now there are 5 models, 5 different models that were able to classify these values and then make certain predictions. So model 1 classified this as a 1. If the prediction is right, it is colored as green. If the prediction is wrong, it is red. So if you look at the individual accuracy, this model has predicted 50% times. It made 50% right predictions. The accuracy is 50%. The other model, the accuracy is again 50. For these 3 models, accuracy is 60%. So 4 times out of 10, the model was not able to make the right prediction. Now, let's do one more model, the final model, and let's take a mode. Mode is what? The most frequently appearing value. So out of these 5, what is the most frequently appearing value? 1. 1 is appearing the maximum number of times. Hence, my final prediction becomes 1. Similarly, here, 1 is appearing 3 times. 1 becomes the final prediction. In this case, 0, 1, 0, 1, 0. 0 appears 3 times. Hence, 0 becomes my final prediction. If you take a final prediction as the mode of different models, this is your final prediction. And as you could see, this model has an accuracy of 0.8, 80%. There are just 2 mistakes here, 2 red bars. Rest everything is a green, and hence my accuracy has increased from a 50 or 60% to 80%. So this is how mode is used when you're working on a classification problem for aggregation. So that was all about bagging. Let's go back to our presentation here. So this was all about bagging. The 2 things that you have to keep in mind is number 1, your all models run in parallel. Number 2, base estimators have to be very different from each other, as different as possible, and thus the errors should be independent. So these are a few pointers that you must keep in mind when talking about bagging. That's about bagging. Now let us talk a little about boosting. In contrast to bagging, boosting creates a model by combining several weak learners sequentially. All right. So first, the base model is going to run. The feedback of the first model would be fed into the next model, and it is going to learn from the mistakes that the previous model has made. Every succeeding model would learn from the mistakes that the previous model has made. That is how boosting works. So let us look at this example here. Let's see, these are my actual data points. So at the beginning, we are going to assign certain weights to each of these data points. At the beginning, they are going to be assigned equal weights. So each of these have been assigned a weight of 1 here. Now this data goes into your base model, and this is the prediction. These are the predicted values. Now the first, second, third values are predicted right. This yellow one means it was predicted wrong. And then again, 4th and 5th were predicted right. So this is your prediction from the base model. There is one error. This 4th value was not predicted right here. What would happen in the next model? The weight of this incorrect prediction is going to change. The algorithm is going to increase the weight of this wrongly predicted observation. So rest everything is going to remain 1. This is increased to 5. So next time when the model runs, it will pay more attention on predicting this one right. So the next model, you would see that now the 4th one has been predicted right. However, this is the 6th one, the final data point is predicted wrong. So in the next model, it will increase the weight of this one. So this keeps on going and going until the training errors, they are below a certain threshold, the entire process keeps on repeating. That is how boosting works. So the main difference between bagging and boosting is bagging is all about parallel execution of models. There is no such concept of error or learning from errors in bagging. On the contrary, boosting is all about learning from the errors made by the prior models. So whatever has happened in the base model, on the basis of that, new weights would be assigned, more weightage are given to the incorrect observations, and then it keeps on repeating these steps until a certain threshold is obtained. That is all about boosting algorithm. Now, talking about the differences between these two, bagging, as I said, all weak learners are built in parallel. Boosting is about successive learners to improve accuracy from the prior weak learners. In bagging, equal weight to each learner, we have previously seen when we were looking at this example here, we took an average. We never took a weighted average here, right? So equal weightage was given to model 1, equal weightage was given to model 2, despite of the differences there in that are there in their accuracy or error. Now this is the error is high for this one, but we are not discriminating between the two models. Equal weightage given. That does not happen in boosting. Better models are given more weightage to evaluate the final performance. Bagging, as I said, independent samples. In boosting, the subsequent samples have more of those observations which have relatively higher errors. As I said, it is an error-based learning technique. So the subsequent samples will have more observations which had relatively higher errors. That is how these samples are not independent in boosting. Bagging helps to reduce the variance of the model. Variance of the model means a model suffers from variance when the model is overfitting, when it is too complex. So if your model is too complex, it works well on the training data, but when the model is exposed to unseen data, the performance is not very consistent. In that case, you could go for bagging. On the other hand, your bias can help you, boosting can help you reduce the bias of the model. Bias means the model is too simple for the problem. Model is not able to capture enough information from the data. Hence, it is too simple. Thus, bias is there, and you could use any boosting algorithm to reduce the bias of the model. Some examples of bagging models are, there is a bagging classifier, which is very popularly used. There's random forest. Boosting algorithms are adaptive boosting, gradient boosting. Now, the basic approach would remain the same, but these algorithms would have some small tweak which would make them different from each other, and that's it. But the basic working would remain the same, just the way I explained. All right, let us go for a live demo now. I will answer all your questions towards the end. Let us quickly go through the working of one of the algorithms here. So it's a small example. I'm sharing my screen again. This one. So we are going to work with the very popular breast cancer data set, which you could load from the sklearn library datasets. The other important module which we would use is train test split, which is used to divide your data into training and testing. Then you would use a decision tree classifier. Decision tree classifier is going to be your base model, the base estimator. And then the bagging classifier, one of the algorithms that we just talked about. All right. So I'm going to create X and Y from this particular data set. X would be the set of all the independent variables. Y would be your dependent variable, target variable, the variable that you wish to predict. All right. X and Y are defined. Next, we divide our data into training and testing data sets. So X would have its own train and test data set. Y would have its own train and test data set, and we will use a size of 25%. 25% of the data is reserved for testing. Rest 75 we are going to use for training. So here we have called a simple decision tree classifier with the max depth of 3, and we want to generate it randomly. Samples would be generated randomly. And this is my base estimator here. Now I'm going to use this base estimator to call bagging classifier. This is how we call a bagging classifier. Now let us look at some of the hyperparameters for a bagging classifier. The first one is base estimator. You have to provide a base estimator. You could any classification or regression algorithm could be used here. You could use logistic regression. You could use a decision tree. Any base model that you wish to explore, you could use. For now, we are going to use decision tree. We have already created a decision tree here. Number of estimators. So as I told you, there could be n number of models which run in parallel for the final prediction. This number you could define here. For now, we are going to keep it 5. We don't want this piece of code to take long to run. So we'll keep it 5. 5 number of base estimators we are going to run. Max samples is the sample size. The maximum number of samples to be withdrawn with replacement. So which is going to be 50 here in this case. And bootstrap true means that sampling is going to be done with replacement. So this particular feature, bootstrap, you have to set it to true. And thus we call the bagging classifier here. Base estimator is true. 3. My decision tree classifier, number of estimators is 5, max samples is 50, and bootstrap is true. And then we fit this particular object to our training data sets, X train and Y train. Fit it to the training data set here. And next, all you have to do is print the scores. So let's just restart and run it again. So here we have imported all the necessary libraries, loaded the data set, and created a simple base estimator decision tree. Next, we are done with the bagging classifier and the performances. As you could see, training score is the accuracy score on the training data set is 94.3, and the accuracy score on the test data is a 96.5%. So these both are very close to each other. Hence, we do not see the model suffering from overfitting or underfitting in this particular case. And that is what the overall objective of using a bagging classifier. So I guess this was a simple example. You could try this out with a much more complex data set also. And you could try different base estimators here. Try to play along with these hyperparameters as much as possible. There are other hyperparameters as well. For now, I'm going to stop sharing my screen and let us see what questions were asked. Difference between bagging with decision tree and random forest. Random forest, Ashwin, is another ensemble technique, ensemble method algorithm. Your decision tree is a simple base algorithm, while random forest is one of the ensemble methods. That is, the entire approach is very similar to bagging. The only difference is with random forest at this step. Let me share my screen again. Hold on. So if you could see my screen now, what happens with random forest is, just like we have withdrawn random sample of records from the data, in random forest, at a certain point of time, or for one of the models, you would also subset the number of features. So subset of sample records plus subset of features. Only a subset of features would be used to generate a tree. Then another subset of features would be used to generate another tree. So that is the basic difference between bagging classifier and random forest. Rest everything works like this. If the samples are drawn with replacement, won't that mean that the random samples are not independent? If the samples are drawn with replacement, that means that random samples are independent of each other. No, Aditya, I guess you are thinking it other way around. If your samples are withdrawn with replacement, then they are independent of each other. Let me just scroll up the chat window and okay, the accuracy changed because if you had observed, we are using a random parameter, random hyperparameter. So every time random sampling is done to withdraw samples from the data, and hence the numbers are going to change a bit. Okay. Recording, I guess, yes, you can. This would be there on their YouTube account. You could access this recording from there. Voting classifier is a classification algorithm. So your decision tree is a voting classifier. Where does majority voting comes in ensemble techniques? So who has asked this? Maria, just now we saw that example where we choose the mode to come up with the final prediction. That was nothing but the voting mechanism. The class out of 0 and 1 with the maximum number of votes gets the final prediction, once the final prediction. So since 1 was up for the first record, once was appearing the maximum number of times, one got the maximum, label 1 got the maximum number of votes. Should we constrain base model before passing it to bagging models? For example, you have constrained. You need a base estimator. That's it, Srinivasan. You would have to declare a base estimator. You can either do it separately at the top, or you could even declare it inside the hyperparameters. Mahesh, bagging score is your accuracy score. Notebook would be shared to you. Code file would be shared. Okay, difference between test set and validation set. So what happens is, you usually, so how do I explain? Okay, so what happens is the data is when you have to deploy your model in production, your data should be divided into 3 sets: train, test, and validation. Validation data set is something that you wouldn't allow your model to see until you are sure of the performance and sure of the fact that this is the final model that you wish to deploy in production. Why? Because data leakage is something that happens when your model is exposed to the test data. So when you are exercising hyperparameter tuning, you test it on the train. First, you evaluate the model on training data set. Then you evaluate the model on test data set. You observe the performance and then go back, change the hyperparameters again evaluate the performance. So in a way, you are tweaking your model basis the test results. You would wish to keep one data set that is completely unexposed to the model to evaluate it once again before it is deployed in production. For that, you keep that validation set. That set is never exposed to the model until and unless you're sure that this is the final model that I wish to deploy. Clear, Keshav? Godfrey, I guess they have shared my LinkedIn profile with you. It is there on the LinkedIn. The link to the LinkedIn profile is shared on the registration page, so you can follow me from there. Bagging with decision tree random forest, we talked about it. What else? How to find weights for model. So I'm sorry, Nadi Katla, your question is not very clear. Which weights are we talking about here? Yes, Chucks. Even the ensemble methods need to be optimized by hyperparameter tuning. There are times when your data is such that only using ensemble methods wouldn't be sufficient for the problem. In that case, there are certain hyperparameters which you could use to tweak the performance. And then again, you should know which problem do you want to solve. Is it overfitting or is it underfitting? Can we do hyperparameter tuning in bagging for the model running in parallel also? Can we do? Yes, you could do hyperparameter tuning for For the base estimator, are you talking about the base estimator here? At least that is Ashwin. What I understand is if you could do hyperparameter tuning for the base models, base estimators, yes, you could do that. While you are initializing your base model, you could use certain hyperparameters and then do it later for the bagging classifier as well. However, be sure that it is not you're not increasing the complexity too much. Oh, you don't have to define those weights. Those weights are assigned by the algorithm itself. Can we use two different types of CNN, VG19, GoogleNet, and Ensemble approach? Different types is only possible in stacking. Who has asked? Nuzat, it's only possible in stacking. You cannot use different kinds of methods in bagging and boosting. Bagging and boosting works with similar kinds of algorithm, just one of them. Ensemble methods can handle the problem of class imbalance. Interesting. Well, it depends actually. So if usually there are other techniques that we use to solve the problem of class imbalance. First thing that you should keep in mind is which particular measure do you wish to target? Is it the overall accuracy that you would want? Is it recall or is it precision? So if it's one of them, either recall or precision, then try to go with oversampling or undersampling techniques first, and then on the top of that you could use an ensemble model. However, if the purpose is just to get overall accuracy, then I guess going with any ensemble model should help. Is there a situation where there is no errors on the previous model? If yes, do we still need to go ahead with the boosting? The situation that you have described here, that there is no error on the previous model, that is too hypothetical. I do not believe that that is ever the case. So prediction is always prone to errors, Peter. In bagging classifier, if we have even number of models and equal number of frequency of classes, how mode will work? If we have even number of models and even number of frequency of classes, how the mode will work? What is even number of models and frequency has anything to do with mode? How will the aggregation work in this case where all records are unique in each bagging model? Even if all records are unique, Udish, it always takes an average of all the predictions. You do not necessarily have to have same records there. The objective is to take an aggregation towards the end. Okay, in customer satisfaction prediction, which score we have to focus, precision or recall? That's an interesting question. Let's talk about this one. So customer satisfaction prediction, I assume that it is whether the customer would be satisfied or not, right? Now, let us define our precision and recall cases here. Let us define false positives and true false negatives here. So what would be a false positive? Your system, your model identifies that the customer would be satisfied, wouldn't be satisfied, false positive. Yes. So it is your positive here being that the customer is satisfied. Your model identifies the customer is going to be satisfied. However, it is not. And a false negative would be model says that the customer won't be satisfied, but the customer was. So these are the two kinds of error, false negatives and false positives. Which one is more harmful for the company? The first one, where you are telling the model is going back and telling you that the customer would be satisfied, but in actual, the customer is not. So a false positive is more harmful for this kind of a model. And which measure do we focus on while we talk about false positives? Precision. So here in this case, you have to target precision. Are there more questions? Please explain once more about production. What about production? I'm sorry, could you elaborate your question? If you wish to optimize hyperparameters in ensemble learning, what are the ways in your opinion? So it all depends on the kind of problem that you're dealing with. There are quite a number of hyperparameters. Let me share my screen. I don't think they send recordings to the mail IDs. Vikas, are you talking about production or prediction, and which prediction are we talking about? If you could clarify, I shall explain it once more. All right, hyperparameters with, let's talk about bagging classifier here. Just give me 1 minute. All right, sharing my screen. Hope everyone is able to see my screen. When we talk about bagging classifier, these are all the parameters that you could play with. Number of estimators. If you keep on increasing the number of base estimators, you would eventually decrease the learning rate, but you have to look for a threshold. Till that point, you could probably get a good number of estimators that will make your model even more stronger. The number to be drawn, you could play along this one. The number of features to be drawn from X to train each base estimator. You could also give the number of features to be drawn from this. The other one, which is very useful, is this out of bag sample score. It's a Boolean value. You could either, by default, it's always false. You could set it to true. What is out of bag samples here? So what happens in, especially in random forest or in bagging, what happens is when you are creating these samples, there are some data points here in the training data which do not show up in any of these random samples. Since we are sampling with replacement here, there are certain data points which would not show up in any of these samples. You could use that chunk, the set of data points, for further evaluating your model. When this prediction is done, test your prediction or test your model, test your final model on that data that was not selected as during the process of sampling, and whatever error you receive from that evaluation, use that error as a feedback to construct the tree again or construct the algorithm again. So since that chunk of data was not selected, that chunk is called in terminology that is used as out of bag. Okay, the chunk that was not used during the sampling for training the models is called out of bag data. When you use that out of bag data to evaluate the model further, you get an out of bag error. That error can further guide the building of a model, the construction of the algorithm. All right. So if you set this out of bag score as 2, the out of bag sample is used to estimate the generalization error, and it can further enhance the model performance. So this is one of the coolest hyperparameters that one could use. Yeah, these are all of them. For imbalanced classes using SMOT, would it be better? Yes, you could. SMOT is an oversampling technique. You could use SMOT, Vishal. It is one of the effective methods. What is the difference between gradient boosting and adaptive boosting? Okay, after answering this question, I will talk about precision and recall. Okay, when to use precision and when to use recall, I will talk about that. Let me first answer this question, the difference between gradient boosting and adaptive boosting. Adaptive boosting is very similar to the traditional boosting algorithm that we just talked about. Each model learns from the error made by the previous model. That is how adaptive learning also works. Gradient boosting differs in a way that the model, the succeeding models, they no longer predict the actual value, rather start predicting the residuals. Residuals means the errors made by model. So gradient boosting algorithms, they learn by predicting residuals and they try to minimize residuals. While they are predicting residuals, they try to minimize the residuals as they proceed on with every succeeding model. They try to bring it down, and that is the only difference. Is there any situation sampling done nothing in unbalanced data? I'm sorry, Anju, I didn't get your question. Okay, let us talk about precision and recall now. So precision is two things that you got to remember here. Number one is how do you define your false positives and false negatives. False positive is your model predicts a positive while the actual value was negative. Model predicts a positive when the actual is negative. False negative, on the other hand, is model predicts a negative, which is false, which is not right. The actual value was positive. So you always got to know how to define these two errors. Once these two errors are defined, precision is always affected by your false positives. If false positive is something that is affecting your algorithm so much that you cannot bear to have a false positive in your model, that is when then you should work on the precision. On the other hand, when false negative is something that can hamper your model or your solution too much, that is when you must target recall. All right. Are ensemble methods affected by outliers? It depends, Keshav, not so much affected by outliers, but again, it would depend. Okay, what kind of noise is present in the data? It is what happens when outliers are present is your model tends to overfit. And what concept are we using in ensemble techniques? We are using the concept of aggregation and generalization. When we generalize, we are already when we aggregate, we are already generalizing the effect of outliers on the data. So they are not so much affected by outliers, but again, in case the noise is such that it is not, it's creating a bias or something like that, then it might. If we want to reduce false positives, we got to make sure precision score is high, right, Arvind? Everyone, please do fill the feedback form before you leave. Should outlier treatment be done in all ensemble methods? See, what happens is when you are using ensemble techniques on decision trees, you're using decision trees or random forest, such algorithms are very robust to outliers. They're not that much prone to outliers. So you could skip your outlier treatment if you're going with a random forest or Bayesian classifier. They are anyway very robust to outliers. But it is always a good exercise to be aware of what kind of outliers are present in the data. Don't just ignore them. Heart disease prediction, which ensemble technique is effective, ma'am, to increase the model accuracy? So heart disease prediction is a classification problem. You could start with bagging, try hyperparameter tuning on bagging. You could then probably use random forest, hyperparameter tuning on random forest. These are some of the models that you could try. What are the methods to target, recall, and precision? Methods to target, recall, and precision. So there is no such method, Amina. It is an exercise where you have to be very well aware of your data, number one. Number two, while using logistic regression, you could use the ROC AUC curve. You could use the precision recall curve to strike a balance between precision and recall. There are a lot of ways actually to be aware of what is happening. And then there are ways to correct that. Is bagging most suitable for regression? There is no such concept, Arvind. You could use bagging for regression as well as classification problems. there is no such concept of most suitable for any of the two problems. Explain how to optimize hyperparameter, whether by partitioning method or cross validation. Cross validation is again, you do it, grid search plus cross validation is done to reduce overfitting. I am not sure which partitioning method you're talking about here, but cross validation is a good exercise that you must always do. Thank you, Bashwant. If I'm not able to answer any of the questions, you could ping those questions again. Accuracy changed that I explained. Code file, I'll try to share it with you. Two different CNNs, no different algorithms could be used. It can only be done in stacking. How to be consistent in data science even when on job. Keep learning. Chucks, I fear I'm not really able to understand your question. How to optimize hyperparameters by cross validation is what you're asking. Arvind, I will try to host a session. I'll talk to the analytics team and let's see if we can have a separate session for ROC, AUC, precision and recall. Yeah, that would help. Because I'm available on LinkedIn, you could connect with me on LinkedIn. Voting classifier, Nadikatla, it is the same algorithm that we just talked about where we were using the mode. Mode is nothing but we were taking a vote. Whichever class has the maximum number of votes, that wins. So it is the same thing. The classifier that we looked at in the example on that Excel sheet, that was a voting classifier. It's kind of 6 lakh rows of data, which is better oversampling or undersampling. I would say undersampling, but then it would depend. It depends on a lot of other factors. You could try with undersampling. Undersampling is something which is not very recommended because we are losing out on a lot of information. LinkedIn profile, someone has pinged the LinkedIn profile handle above. Let me ping it again. This is my LinkedIn profile handle. What can I do if my model accuracy is not very good? Keshav, again, if the accuracy is not very good, you will have to figure out what is the problem. Is the model not doing a great job on the training data itself? If that is the case, then there is underfitting. Yeah, your model is too simple to capture the information. In that, you have to increase the complexity of the model and find out ways to do that. How do we increase complexity of a model? Use a more complex, strong algorithm. Maybe your algorithm is too simple for the problem. Use more data, bring more data points into the problem. So those are the ways which you could use to make a model even more complex. If your accuracy is good on training, but not that great on the test data, that means that the model is overfitting. It is not generalizing very well on the unseen data. So that's the case of overfitting. How do you get rid of overfitting? There are a number of ways. You could try bagging to overcome overfitting. You could try cross validation. So a couple of ways that you could do to overcome overfitting. All right. Thank you so much. I have better things to do, Satish. Thank you. Thank you, everyone. Thank you for this lovely session. Hope I've managed to answer most of the questions. Thank you.